Okay, so let's look at more examples regarding stick diagrams, because these are very helpful for you guys to design the layout before you open that EDA software, right? You want to handle it first. All right. It's Friday again. Nice. All right. Good life is coming in a few years for you guys, so no worries. You'll find a job and enjoy your life. Undergraduate is tough. Graduate school is better than undergraduate in my mind, because you are getting paid. If you are pursuing a PhD degree, it's usually, tuition is covered and give you a little stipend. You can cover your rentals and food as well. Undergraduate is just tough. It's rough. You have so many classes to take at the same time, and sometimes you have to work. Difficult time. Right. For example, inverter. Since we mentioned about the parallel NMOSes, parallel PMOSes are pretty simple, like this one. You just short them together. That's a parallel NMOS. So an inverter looks like this. Right? And since we just mentioned that, this is a stick diagram for the PMOS, and this is a stick diagram for the NMOS. So when you are designing the stick diagram for the inverter, it looks like this. So you have to draw the top rail and the bottom rail first. Right? And then PMOS on the top, NMOS at the bottom. Why? Why not swapping them? Yeah. PMOS is 1? Yes. Because PMOSes are good at passing ones and NMOSes are good at passing zeros, right? So that's why you have a complementary MOSFETs for the circuit. So all the PMOSes are being laid out on the top and all the NMOSes are being laid out at the bottom. Because the bottom rail is the ground rail, ground line. Introduce the wire here. So definitely the two gates are shorted together. And so you can just directly draw one gate. So the layer for this gate is called polysilicon. This is a polysilicon layer. So we are going to introduce all the different layers in the CMOS IC chip from the cross-sectional view in the next few weeks. But now just let you know, guys, the gate is not metal. The gate is a polysilicon. Has a little bit higher resistance compared to metal, since it's not metal. It's not as good as metal in terms of conducting charges. Since these two gates are shorted, so you can directly just draw one polysilicon. And so that wire here is this one. And so the current runs through the channel, and current runs through the channel reaches the drain of the PMOS, and you short the drain of the PMOS to the drain of the NMOS, and the current flows through here to here, and to the source of the NMOS, and then to the ground. So the inverter can be represented by this stick diagram on the paper. So where's the input, where's the output? So that's input, right? That's a polysilicon, that's a gate. And now it's a wire, it's a metal. So you need a metal wire, and because the polysilicon is actually relatively lower compared to the metal, so if you cut it here like a pie, so this is on a silicon wafer, right? Cut it and look from the side, the cross-sectional view. That's a wafer, silicon wafer substrate. And that's silicon dioxide. That's an insulation layer. And the polysilicon is being deposited in the middle of the first insulation layer. And you can drill a hole, it's called a via, to the upper layer. And you can have a metal here. It's called metal 1. That's how you can make the connections. That's a cross-sectional view, right? So the silicon wafer I showed to you, the silicon die, if you can cut it and look from the side, so that's a cross-sectional view. You have a polysilicon layer as a gate and drill a hole to connect the polysilicon to the upper level, which is a metal 1 layer. So this is metal 1, and you can connect the signal to metal 1 and send it to the input of the inverter. And here's the output. You can also use metal 1, doesn't matter. That's out. So you don't have to use different colors in your hand drawing. If you like, which is good, but it's not required. That's a metal. So input output, right? So that's the inverter stick diagram. What about NAND gate? The NAND gate. So NAND gate looks like this. Similarly, you need 2 rails. And these 2 PMOSes are in parallel in series. Are they in parallel or are they in series? These 2 PMOSes. Parallel, okay? But when you are drawing that stick diagram, so the stick diagram here represents the layout, just keep in mind. So remember, I think, did you do that? Yeah, you did it on Tuesday, right, this week, for the NMOS and PMOSes, right? So when you drag a PMOS or NMOS from the library in electrical VLSI, you can, so it looks like something like this, right? That's a PMOS. And for this one, so this represents this one. So when you are drawing an inverter, you need a NMOS at the bottom. And you have a metal on the top, another metal rail at the bottom. Right? So we are trying to laying out the inverter, which can be physically fabricated on the silicon wafer. Right? You want to make the connections. So this one, you need a metal one to connect this contact to the top VDD rail. And then here's the drain. Make the connections. And short these 2 polysilicon together and introduce the wire that's in and that's out. And that's the inverter. So if you compare this one, they are very similar. That's why when you are trying to design the layout at the very beginning, you want to use stick diagrams instead of just drawing every single transistor. It takes time. So you want to use stick diagram, which is simple compared to this one. When it scales up, you will find out this is very useful. And you can simplify the layout by using stick diagrams. So now let's look at NAND gate. I mean, before we lay it out, we want to design the stick diagram first. So these 2 are in parallel. They are thinking about I mean, how can you make it in parallel? Because we laid out all these ones like this, right? So we are thinking, hey, just make two PMOSes in parallel. So I have one PMOS, I got another PMOS, and the two gates are not shorted. I just make these connections so they are in parallel. But that's not a good practice. We usually don't do that. It's taking a lot of space by doing that. So the way we lay out parallel PMOSes is something like that. We still put them together, and it seems like they are in series, but actually they are not. So you are wondering, you just put the two PMOSes in series. How can you tell like they are in parallel? It depends on how you wire them up. How can you make these two in parallel? There are two ways to do it. First, introduce the voltage VDD to the middle one and short these two diffusions or contacts. So these two PMOSes will be in parallel. Look at it and tell me if it's true. So current is being introduced from the VDD, from the power source. So current flows through and into the shorted terminal here first, and then being split in two branches. So they are in parallel because these two currents will merge here eventually. Is that correct? So they are in parallel. What's the second way to do it? I can introduce the one in the middle and then merge them on the two sides. If I just flip it, it's still the same structure, right? Just imagine you are flipping them. So you get two on the sides and merge in here. So they are still in parallel. It's the same circuit, equivalent. If you do DRC and LVS or NCC, comparing this one, comparing this layout with this schematic in electric VLSI, it's going to report zero errors. They match with each other because they're the same thing. Doesn't matter which one you want to use, they are equivalent. Let's keep with using this one. So what about NMOSes? Still, just put them in one string, in one line. Two gates. And now they should be in series because of the non-gate structure, schematic, right? That's easy. You just need to short the drain from these two PMOSes to the drain of the first NMOS and short it to the ground. So they are in series. It is one line, one current branch, right? So the next question. So what about the gates? How do we want to label the signals? Does that matter which is A, since this is A and B, right? So this is A, not B. Does it matter which is A, which is B? It doesn't actually matter. They're interchangeable, right? Doesn't matter. So what if I label this one as A, this is B, this is B, this is A? It's fine, but just not ideal. But will that match? Here's the thing. If you do LVS, layout versus schematic, or in electric VLSI, it's called NCC, just doing a layout and schematic matching check. If I do this, is it going to pass LVS or not compared to this guy? Why? So the critical thing here is for A. You look at A is being shorted to the first PMOS, right? So if you make this connection, the current runs through the first NMOS is this guy. So you have to have this signal line as A. Otherwise, it won't pass LVS. So for here, it matters. So this one must be A, because this one is A. That's the first PMOS underneath the, this is the first NMOS underneath the PMOSes. And this is the first NMOS underneath the PMOS. But these two doesn't matter at all. These are in parallel, they are interchangeable. So if this guy has to be A, this one has to be B, right? And do you still want an A here, B here? It's not ideal, right? You probably want to swap them, even though it doesn't matter, but still want to swap them. The reason is you want to short the gates together. If this is A, this is A, the two gates should be shorted together. And the two gates should be shorted together. And you can imagine if you have A here, then you have two poly layers, they're the same layer, you cannot cross them because it's going to short these two gates. Because they are running on the same layer. You got a poly here as well. The same layer, you cannot get through it. Or if you get through them, you cross the two poly layers, they are going to be shorted, becomes one signal. Otherwise, you have to drill a hole to the top and run metal one on the top, and then come back to the poly layer again. If you don't want to short them together, but it's still going to take a lot of space. So for this case, you have many different options, but you need to be aware of the best practice regarding the space, regarding the length of the poly wires. Sometimes the poly, you can, if you do not have a pretty long poly connection, so distance is not really long, you can directly use a polysilicon. Keep in mind, it's not metal, it's just like more, a little bit more conductive compared to the regular silicon semiconductor. It's just more conductive, but still not metal. So if you have these two, you know, with a pretty reasonable distance, you want to directly short them with a polysilicon, which is fine because you don't have to introduce all these vias and getting a metal and then come back to polysilicon again, right? Because it's not that long, so if you use polysilicon, it's not going to introduce a lot of resistance to it. So they are still the same signal. There won't be significant voltage drops along that polysilicon wire. If you have a super long connection, you know, from here to here on the chip, you definitely don't want to just directly use a polysilicon to make a connection. It's probably a few thousand ohms will be introduced in there. It's like a resistor. It's, you are changing the circuit. So what you want to do, you want to drill via, if you have a long distance, you have a poly here and a poly here. What you want to do is just drill a hole to the upper layer and use metals. And then drill it down to this poly. That's what you want to do it. But do not use super long poly wires. This is fine, you know, it's just pretty short distance. All right, that's for NAND gate. What about NOR gate? Very similar. Two rails, no exception, two rails all the time. Just put them in one string. Still no exceptions, right? Two PMOSes in series. What about here? Two NMOSes in parallel. You have two options, remember? You can either do it like this, or do it like this. So both of these structures will pass LVS for the schematic of the NOR gate. Now let me know which one should be A, which one should be B. For the first one, which gate is A, which gate is B? Yeah? That's A. That's B. Right? So if this is A, this is B, does it matter which one is A, which one is B here? Doesn't matter, but you have a better choice, right? Which one should be A, which one should be B? A here, B here. So you can directly make a connection. Just directly drag it and make the connection. And you're thinking, is this shorting this wire? I mean, you got crossed. Is this shorting this wire? Why? Where is metal 1? Here. The first metal layer. You can use the second metal layer even, but right now it's just metal 1. And this is poly. It's lower. So they're not shorting. It's like running to different floors, right? Not going to short. This one, same. Okay, good. So let's look at a 3-input NAND gate and 3-input OR gate. Still 2 rails, no exception on that. VDD and ground. All right. So 3 transistors, how can I tell? I got 3 transistors, how can I tell there are 3 transistors on the top? Yes, 3 gates. And they're in parallel. How do we make it happen though? One here, and one here. And why? Why is this 3 parallel PMOSes? So these 2 wires are being shorted to the VDD, the top rail. So you can consider them as one voltage node. It's just one metal piece. And it's going to introduce currents from VDD at the same time. And wait. Oh, yes. Then that branch, if you imagine that's just one wire, it's just one metal piece, right? It's one wire. And it introduces currents to here, and it's going to flow in this direction, and also this direction as well. So got 3 branches. Is that correct? It's just like introduce one thing from one common joint and then immediately split it in 3 branches. And it is being split in 3 branches. So that's why these are but not yet, right? So these are being split in 3 branches, and they eventually merge. So these 2 branches merging here, and this single branch merge into here, and still the same wire. So it starts from one joint and got 3 branches and join at one point eventually. So they are in parallel, 3 branches in parallel, and that's going to be the output of it. All right. 1, 2, 3, 4. 4 NMOSes in series. Since you have this output from the parallel PMOSes, it is shorted to here, and that's going to be 3 NMOSes in series. So how do you label the signals? Does it matter? It matters. The order here matters. If you do not follow the order like ABC for these 3 NMOSes, it won't pass LVS. So this must be A, this must be B, this must be C, because this is from the top, like in that direction, ABC. So in that case, you have better choices for A, B, and C's for the PMOSes, right? In the case, just do this. So it's going to be A, B, C. Although they are in parallel, but you have better choices. We're going to have a quiz on this on Wednesday next week. Okay. NOR gates. Three PMOSes in parallel. Oh, in series, I'm sorry. And NMOSes in parallel. So keep in mind, if you need 3 transistors in parallel, whatever is our PMOSes or NMOSes, what's the trick? So literally just need to remember one thing, right? It's like, just do this connection and they'll be in parallel, and that's it. So introduce here, output here, or introduce here, output here, doesn't matter. Just memorize it. All right, that's 3 in parallel, and that's it. So well here, you want to create this structure, right? So according to this structure, I can connect the first one, the third one, and then do this. Will that make it work? Is this going to do the job? Let's see. I don't even have to have this, right? I directly just short these two to the ground. I don't even have to connect these two together. Use the actual wire. So the current is being split in here, here, and here, and 1, 2, 3. 3 branches and merges at the ground. Make sense? Cool. Now let's look at a arbitrary logic expression. So for example, y equals to a or b or c, not and d. So De Morgan's law, of course, is equals to a or b or c, not and d, not, and this becomes split the bar, change the sign. We got a bar on the top, and a or b or c, because we got two bars that are canceled out, and or d bar, and this becomes a 4 input NOR gate. Is it? ABCD NOR. Is that correct? How to design the layout? Yeah, I have to think about it a little bit. It's not that straightforward, but it's doable, very doable. So still two rails, right? And still four in series, right? And how can I make it in parallel? So it works like this. And now let's see if that's true. So that's the same node, same source, same input. And let's see how many branches this signal is being split into, okay? So current being introduced to here, 1, same wire, 2, same thing, 4, 3, 4. 4 branches and merged into one, same wire. So it looks like a string series, but actually they're in parallel, right? So you can save a lot of space. And how to improve it? I mean, it's not even the final version you want to use. So before you do that, look at signal lines. Doesn't matter which is which. The PMOS is definitely has the order, right? Because they are in series. So on the top, this A has to be the top one, which is called, just next to the power line. So this will be A, B, C, D naught. These ones are in parallel, so it doesn't matter. I can directly just short this one to here, 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 and these will be ABCDs. Now you're asking, you have so many power inputs, how to introduce this, or how to export the signal lines. But definitely this is the output, that's easy. You just drag a line in the layout, you just drag a line here like a metal 1 layer and just call it Y, right? Just name it as Y, which is fine. What about the inputs? They are all inside. Do you want to use, for example, I got A, B, C, D, not. I would just want to put everything in a box, right? So it's ready to use. I need the 4 inputs. How do I want to make the connections? It's the same, it's also a subcell for the layout. So you want to use subcells everywhere, right? So that's a subcell. How to export these signal lines to the left. That's a physical circuit. It's going to be a layout, not a schematic. It's just something. It's just representing the circuit connections. But this is a physical layout. It's going to be physically being fabricated on the chip. So you cannot make short circuits. So what material you want to use to connect to the poly? So what are these materials? Polysilicon, right? Gates. Do you want to use polys? Boom, 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 directly? No. It's shorting all the signals, right? You want to use a different layer. So just use metal one from here to here. Definitely it's fine because there's nothing in the middle, right? This one, still metal one. Does that matter? Is this causing any short circuits? It's not. This is poly. So you are good. So you can imagine you probably won't have too much space here because these are metal ones as well. So when you are laying out this guy, you probably want to keep this one short, right? So have more space to wire it up like this. If just really do not have any space left, you want to just make it taller. Stretch it just to get more space, right? All right. Look at another circuit and see how we can design a stick diagram out of it. A or B or C and a D not. So remember how we design a complex CMOS circuit from Monday this week? So we start from, convert everything into a something bar, right? First. And if you have a NOR logic, you need a PMOSes in what on the top? If you have a NOR here, you need the PMOSes to be what on the top? Always think about the NOR gate. So the PMOSes are in series and NMOSes are in parallel. For this NAND, you need a PMOSes in parallel and NMOSes in series, right? Yeah. So now let's draw the circuit first. You need to draw the circuit schematic first and then convert it into layout. Can you directly convert a logic expression to the layout stick diagrams? No. Since you have to look at this. So you can convert it here. Directly jump from here to here is impossible. So I'm going to do the schematic first. A, B, C are in series. And D in parallel. But the NMOS is different, right? You have ABCs are in parallel and D in series. So that's a complex CMOS logic. You can definitely design a logic gate based circuit out of it. It's going to take a lot of space compared to this one. That's what we prefer. This it's faster, smaller, and just better. Okay. Layouts to rails. One, two, three, four. So we need 5 diffusion nodes and 4 gates. Three are in parallel. Three are in series. One is in parallel. How to make it happen? What about that? Yeah, either way. Good. So one line introduced and 2 branches, boom, in series, another single one, and merge to one joint here. So in parallel, they're in parallel. And for these ones, 3 in parallel, 1 in series, how would you do it? Remember, 3 in parallel, we always have, remember how we do that? 3 in parallel, just this, right? That's 3 in parallel. So how we can do that? If I short this one to here, and I start that structure from here to here. So what about the last one? What about D? Can we still get this one in series with the parallel PMOSes? So this one, this part, remember, that's a 3 transistor in parallel, right? The structure. Just keep using that. So we're getting that here. And here's the output. That's the output. So this node is this node. Now, is that true? You agree with that? Okay. And after that, just boom, ground. After that, ground. Done. So we need a connection, final connection here, to the ground. Do we need to short this to ground as well? No. Is it going to pass LVS? Is it going to pass LVS? Not yet, since I haven't connected gates. I just designed a little trap and you just jump into it. Testing, see if you are sleeping or not. How do you want to connect the gates? ABC, do they have an order or not? Yes, in series, and A has to be on the top. So which is A in here? This guy, right? So this must be D. What about these ones? ABC doesn't matter. So is there a better choice? Make sense? I think I have one last example for you guys, and then we are done for stick diagrams. So this is critical. It's very useful. Probably will show up on the quiz. The last one. Y equals to AB or AC or BC Seriously, these are all homemade examples. Okay, you cannot find them on any textbooks. This one, first step, A, B, or merge these two together first. Okay. And what's next? So we have this structure now. Now we can start working on converting this guy to its complex CMOS logic circuit. That's the overall operator, the final operation. So you got two black boxes to be NORed. They're being NORed together. So you need these two boxes in series on the top and parallel at the bottom. But internally, these A and B should be in parallel. So you're getting that's AB, right? And then this guy at the bottom. That's for the PMOS. Is that correct? All right. Then NMOS is A and B. So these two boxes should be in parallel, and these two are in series. That's A and B. So in here, you got A, B, and C. Right?
So when you run an envelope part of the CMOS, it's always inverted from the PMOS.
Yes. So inverted means you got like parallel here, you need a series here, right? You got series here, you need a parallel here. Yep. So now let's see how we convert it into its layout. Definitely not that straightforward. Two rails. How many? 1, 2, 3, 4, 5. So although they are the same signal lines, but you still need since you cannot simplify this further, can you? You can't. So still have to keep the signal lines, although they are the same signal lines. Right? So you have 5. Not 3, 5. I think it's gonna be better if you, because these two, this black box here and this box, they are interchangeable. You can flip them or you can swap them, right? There's no difference. So when you are designing the layout, I think I preferred looking at this one first. So let's just swap them. It should be the same, I guess. let's just thinking like we have swapped them already. And so if I introduce the line here, so it's getting A and B. So right now this part is on the top, okay? So it's directly connect to the VDD. So I get A and B here, and then I short this guy to here, and then connect these two guys together, and that's the output. And now let's see if that's true. This line, so now the circuit has been changed, okay? So this part is on the top, this is at the bottom. I just swapped them, right? So starting from the top, I got A, B in series, AB in series, and in parallel with this guy. So this guy will be C, right? And because that's one branch, that's another branch, so that's the output of these two branches. And now remember this is on the top, so the output here will be fed into here. And you need the two parallel PMOSes. So that's the merged points. And you just need the two parallel PMOSes. And that's the output. Is that correct? For the NMOSes, so I got three branches first. So actually this is what we're going to use for the schematic. Double check. Yep. So we don't have to swap anything here at the bottom. So directly from the top, that's the output from the PMOSes. And I will connect this one to here and here. And then this one here. And here. Now let's verify it, see if that's correct. Output from the top PMOSes, one line, two line, so two branches. 1, 2, 3. So these two are in parallel, so these two will be A and B, these two, right? And merged to one point. And so what is this? Yeah. And then go to the ground. Then go to the ground. No problem here. So what about the other line, the other branch? So we just went through this guy, right? So here, A, B merged. Back to C. And go to the ground. Look at here, this guy, this point, has 3 branches, not 2 branches. The same voltage join. 3 branches. So that's why you got 1, 2, 3. And the one on the right hand side fed into C. But the one going to here flows through A and B in series. And then goes to the ground. No more other examples. That's the ultimate version. So in when you are designing ICs, sometimes you will have to know how to convert the logic expressions into stick diagrams in order to simplify the circuit. But if the larger scale of circuit, you will never do this. You just code it up. Verilog, right? VHDL, just code it up. All right. See you on Monday.